Hello everyone, I hope you are doing good. So welcome to my channel, Snowflake Data Genius.
If you're joining us, it's probably because you're facing a massive problem. I mean, it's a problem that pretty much every modern company is just drowning in.
The unstructured data mountain.
Exactly.
It's so true. We're not talking about your nice, clean, structured transactional tables here. We're talking about the messy stuff.
Right.
The reports, the legal documents, all those internal meeting transcripts, customer support logs, PDFs. It's, all of the actual knowledge that's just locked away in these massive, messy text fields all over your data cloud.
And it's valuable, but trying to find one specific little nugget of information in there manually, it's just impossible.
It's a needle in a haystack.
And so you think, okay, I'll fix this. I'll build a custom search solution. And that's where the real pain starts, isn't it?
Yeah, you're basically signing up for an engineering nightmare.
You really are. I mean, we're talking weeks if you're lucky. More often, it's months of development time. You have to figure out how to manage these separate external vector databases.
And then spin up and scale all the infrastructure just for model serving.
Then you've got to choose and, fine-tune these incredibly complex embedding models and then maintain custom data pipelines just to get decent sort of fuzzy search results that understand intent, not just keywords.
It's a huge lift.
Yeah.
And it's not your core competency. It creates all this unnecessary architectural complexity.
Right.
And, historically, you had to make a really painful choice. You had to ask, do I use traditional search, which, okay, it's fast and reliable for exact matches, but it misses all the context?
Totally.
Or do I go all in on pure vector search, which is amazing at understanding context, but sometimes it just completely fails to deliver on those critical exact lexical matches.
But if you, our listener, are already operating inside the Snowflake Data Cloud, there is now a really attractive shortcut that just removes all of that complexity.
And it's built right where your data already lives.
It's called Snowflake Cortex Search.
Yeah. And Cortex Search is essentially Snowflake coming in and saying, look, we'll handle all the complexity of hybrid search for you. It's designed to deliver that high-quality, fuzzy search, combining the power of semantic understanding with keyword accuracy, all natively inside the platform.
But you can generate a hybrid search index in minutes.
In minutes.
Yeah.
And manage zero dedicated infrastructure.
Yeah.
And, maybe most importantly, the index actually keeps itself fresh automatically as your source data changes.
That promise of zero external architecture, I mean, that just changes the entire total cost of ownership equation for search, doesn't it?
Completely.
So our mission today for this deep dive is to unpack this service really thoroughly. We need to understand what Cortex Search is, how its unique, high-quality, three-stage hybrid architecture actually works, and what its core uses are.
Specifically RE and enterprise search, right?
Exactly. And then, where the rubber meets the road, we'll cover the practical steps, the cost implications, and those really crucial limitations you absolutely need to know to use it effectively and, just as importantly, safely.
All right, let's do it. I think the best place to start is with the definition and the architecture that really sets it apart.
Let's dive in.
So, at its foundation, Snowflake Cortex Search is a fully managed, low-latency search service. And the key is that because it's natively integrated into the data cloud, it delivers this high-quality fuzzy search directly over your unstructured text data.
The documents, the logs, the notes.
All of it. All the stuff that's already sitting in your Snowflake tables and views.
And when we use this term fuzzy search, we should probably be specific. We're defining a system that goes way beyond simple exact matching, right?
Oh, yeah. It means the service can handle a natural language query. You can ask it a full question, or you can use traditional keywords. And what it gives you back is a result set that's ranked based on its relevance.
And that relevance is both semantic, so the meaning,
and lexical, the exact words. And this combined relevance is really what defines its quality.
That quality is the key distinction, I think, because if we look at the limitations of, legacy systems, they always force you to compromise.
They really do. Imagine you're searching a big policy manual. If you use an old keyword search engine and you type in, say, how to start retirement planning, it will only find documents that have those exact words in that order.
It's so literal.
It's completely literal.
Yeah.
It lacks any context to understand that a document titled 401k Enrollment Guide is exactly what you need. That's the semantic failure of traditional search.
Right, and then you have the pendulum swinging to the other extreme, pure vector search. And vector search is amazing at meaning. It would absolutely find that 401k document based on the concept of retirement.
No problem.
But now imagine you're searching for something very specific, like a unique product identifier. Let's call it SKU 90210 alpha.
A pure vector system might see that super specific term and decide it's less semantically interesting than a broader concept, and it could actually prioritize other documents, potentially burying the exact lexical match you desperately need.
And that's precisely the problem that this core innovation, the hybrid search architecture, is built to solve.
Exactly. Cortex Search doesn't make you choose between vector and keyword. It fuses them together. This ensemble approach combines vector-based embeddings, which capture all that meaning and context, with that traditional, super reliable keyword lookup.
So you get semantic flexibility and lexical accuracy at the same time.
Simultaneously. And the beauty of this system is that it's not just a simple union of two searches. They add a final step that fine-tunes everything using something called semantic re-ranking.
Okay, we'll definitely have to dig into that.
Oh, we will. But this three-part process, it runs on every single query, giving you high-quality, prioritized results right out of the box. You don't spend weeks trying to figure out weighting algorithms or anything like that. Snowflake handles all the complex retrieval science for you.
It's designed to minimize the time from I have this mountain of messy text data to I have an intelligent search bar that actually works.
And the immediate quality that you get from this ensemble approach is what really reduces the friction of adoption.
I do want to push back a little on this premise of zero infrastructure management, because for anyone listening who has battled with dedicated vector database clusters,
Oh, I've been there.
we're talking about managing separate servers, model serving endpoints, auto-scaling groups. The idea of this being fully managed is, frankly, revolutionary. Are you truly saying, we just point Snowflake to the data, and it handles all the index building, all the updates, and all the serving capacity without spinning up a single external VM?
Yes. That promise is held firm because it's natively integrated. Zero external infrastructure management. The entire service.
The whole thing.
The whole thing. The compute needed to create the embeddings, the specialized multi-tenant serving layer that holds the index and answers your queries, it all scales automatically within your existing Snowflake account boundary.
That is a massive TCO benefit. You're just eliminating the licensing, the management, the personnel costs of maintaining a whole separate complex external stack.
And beyond just cost, it dramatically simplifies your security profile, doesn't it?
It has to. The data never leaves the Snowflake environment, so you don't have to worry about external network configurations or data egress controls or managing a whole separate set of security credentials for the search database.
Exactly. It just seamlessly adopts your existing governance model. Your Snowflake roles, your privileges, your access controls, they all apply inherently to the data that's being indexed and queried.
Okay. And speaking of maintenance, one of the biggest headaches in custom search is keeping that index synchronized when the source documents change. If I update a legal contract in my source table, how do I make sure the search index reflects that change within minutes without constantly running these huge, costly, full rebuilds?
This is where Cortex Search leverages some of the most powerful underlying technology in Snowflake.
Yeah.
It uses this change tracking capability, which is actually the same engine that powers dynamic tables.
Ah, okay.
And that enables these incremental real-time updates without any user intervention at all.
And this brings us to that crucial concept of target lag, right?
Target lag is basically your definition of freshness. You tell Snowflake, I want my index to be at most, say, 1 hour behind the source data. Or if you need near real time, maybe you set it to 5 minutes.
And Snowflake just handles it.
It handles the orchestration automatically. It monitors the source data for any inserts, updates, or deletes. And when those changes happen, it uses its internal change tracking to process and re-embed only the rows that were affected.
Just the changed rows.
Just the changed rows. It updates the index incrementally to meet your defined lag target.
So let me get this straight. If I have a 100 million row index and only 2 rows change in an hour, Snowflake avoids that massive, costly rebuild and just handles those 2 rows.
That's it.
That has to be a massive performance and cost optimization.
It's the absolute cornerstone of its performance and efficiency. It eliminates all that manual work of building complex ETL or batch pipelines just to keep an index in sync. It means your index is always optimally fresh, and you're minimizing the compute you're consuming for index maintenance.
Okay, let's unpack this hybrid process in forensic detail. We know these high-quality results are not an accident. They are a function of a very tightly engineered 3-stage pipeline that executes every single time a user runs a search query against Cortex Search. Let's walk through the magic here.
Right. The process starts with two parallel retrieval paths, which are then followed by a final, very intelligent refinement step.
Okay, two paths at once.
So stage one is vector search, or what we can call semantic similarity matching. When you input a query, let's say you type, explain the latest compliance rules for European data. The system first uses the embedding model you chose.
Which we'll get to later.
Which we'll detail in a moment, yes. It uses that model to convert your text query into a high-dimensional numeric vector. And this vector is designed to mathematically capture the query's underlying meaning and context.
And for you listening, that vector dimension is really important. We're talking about hundreds or even 1,000 dimensions. It's a list of 768 or 1324 numbers that positions your query in this vast conceptual space.
And the power of this is that texts with similar meanings, they naturally cluster together in that space, regardless of the specific words you used.
It's like a map of meaning.
It's exactly like a map of meaning. And that query vector is then instantly compared against all the pre-indexed document vectors. The system performs a similarity search, usually using something called cosine distance, to find the closest document vectors.
So this is the stage that delivers that conceptual retrieval. It finds documents that mean what you searched for?
Exactly.
Let's go back to that dream heist analogy. If I search for dream heist, the vector search stage is what's going to retrieve the document about the movie Inception. Why?
Because the vectors for your query and the document's title and summary, they land very, very close together in the conceptual space of surreal high-stakes infiltration. It bypasses the need for the exact word heist entirely.
Okay, so that's happening on one track. But running in tandem, you said, in a race to find candidates is stage 2, keyword search.
The lexical matching. And I hear people ask this all the time. If vectors are so smart, why do we still need the old way?
That's a great question. And I'm guessing the answer is specific precision and reliability.
Absolutely. The keyword search performs a classic full-text lexical match on the raw text data. And this is, it's non-negotiable for enterprise use cases.
Right.
Vector search, while it's brilliant for concepts, it can sometimes misinterpret or just completely overlook highly specific, non-contextual terms. Think about part numbers, regulatory acronyms, specific dates, or rare names.
So if I'm querying for something like ISO 27001 Annex A.12 to 1.2, the keyword search guarantees that if that exact specific string exists in a document, that document will be retrieved as a candidate.
Regardless of the semantic meaning or how the vector model interpreted the surrounding text, it's the critical safety net for that kind of deterministic data retrieval.
Got it. Okay, so stages 1 and 2 run simultaneously. They generate a big list of candidate documents. And you said that combined pool is often way larger than what the user will ultimately see.
It is. And this leads us to the final, and I would argue perhaps the most critical step, stage 3. Semantic re-ranking.
This is the refinement stage. You mentioned it uses a neural re-ranker. Can we peel back the curtain a little bit on what this is doing that the simple distance scoring in stage 1 missed?
We can. So the initial vector search in stage 1 is really fast because all it's doing is calculating the distance between two fixed vectors, the query vector versus the document vector. It's efficient, but it's a relatively crude measure of relevance.
Okay.
The neural re-ranker is far more sophisticated. It takes the combined, filtered list of candidate documents from both stage 1 and stage 2 and passes them through a specialized transformer-based neural network. It's often called a cross-encoder model.
Ah, a cross-encoder. That's a key detail. What does a cross-encoder do that's so different?
Unlike stage 1, which calculates distance based on those pre-calculated vectors, the cross-encoder model jointly evaluates the query and the document candidate together in real time.
At the same time.
At the same time. It looks at the full context of how the words in the query relate to the words in the candidate document. This joint modeling is computationally more intensive, which is why we only run it on a smaller list of the top candidates.
I see.
But it provides a much, much higher fidelity relevance score.
So instead of just saying these two concepts are close, the re-ranker can actually say, based on the exact phrasing and context, this specific snippet from document A is demonstrably more relevant to the user's intent than document B.
Precisely. It acts as an optimization layer. It weighs the strengths of the semantic similarity from the vector search against the importance of the lexical match from the keyword search, and it produces the final, highly accurate, and optimally ranked result list that the user actually sees.
And the ultimate benefit for you, the listener, is that this entire complex, multi-layered retrieval strategy requires zero manual effort on your part.
It's just provided as a service.
That deep dive into the architecture really clarifies why the retrieval quality is so high. So now let's talk application. Why are organizations actually deploying Cortex Search right now? The source material pinpoints two enormous use cases, starting with RAG.
RAG, or Retrieval-Augmented Generation.
Right.
And RAG is the primary driver in the AI space today, no question. As we know, large language models are amazing at fluency, but they are often limited by their fixed training data.
And they're notoriously prone to hallucinating.
Exactly. Generating confident but completely false information.
And RAG is the fix for that. It grounds the LLM's response in actual facts.
Yes. The RAG pattern uses an external retrieval system to fetch current, relevant, and trusted context from an organization's own proprietary data before the LLM formulates its answer. And Cortex Search acts as that engine.
Okay, so give me an example.
All right. An employee asks an AI assistant a complex question about, say, company policy. Cortex Search uses its hybrid capabilities to instantly find the most accurate internal documents, the relevant paragraphs, this specific policy section, and it feeds those snippets to the LLM.
And then ALLM uses that specific grounded context to generate a truthful response, which makes the AI assistant accurate and accountable. The convenience here, I mean, for anyone who has tried to build RAG from scratch, is just staggering.
It is. I mean, traditionally, implementing RAG meant building 3 or 4 separate systems. You needed an embedding service, a vector database, a traditional index, and then all the synchronization pipelines between them.
All separate stack.
It is. But because Cortex Search combines the vector engine and the keyword engine natively within Snowflake, you eliminate the need for those external vector databases for separate model serving, and, most importantly, you eliminate the complex synchronization pipelines between your source data and your search index.
It just vastly simplifies the RAG reference architecture. It turns a multi-vendor, multi-service setup into a single declarative SQL command that runs inside your data platform.
And that speed of deployment and the reduction in the ongoing maintenance burden, that is a core value proposition for RA acceleration.
Okay, so the second major use case is simpler, but probably more common in the short term. Enterprise search and knowledge bases.
This is using Cortex Search purely as a document retrieval tool. It's the high-quality, high-speed backend for any search bar interface you can imagine.
So whether it's embedded in an internal application for employees to quickly look up HR documents,
or serving a massive customer-facing documentation portal, or powering a library of historical research reports, the goal is always the same: fast, accurate retrieval.
and in this case, the end user isn't generating a response with an LLM, they're just getting a ranked list of relevant documents back. But the quality of that list is radically improved because the semantic engine understands why they're searching, not just what words they used.
It just replaces those clunky legacy keyword search tools with state-of-the-art retrieval instantly.
Now, this is a point of frequent confusion that I think we really need to clarify for our listeners. Snowflake has released multiple Cortex services. We have to draw a really bright line between Cortex Search and its sibling service, Snowflake Cortex Analyst. What's the fundamental architectural and functional distinction here?
This is a critical point. The difference lies entirely in the type of data they handle and their primary output.
Okay.
Cortex Search deals with unstructured text data, so you should be thinking massive blocks of text, documents, logs, PDFs. The input is a keyword or free-form question about a document, like find the clause about indemnities.
And the output?
The output is a list of matching records or document snippets. Its primary function is retrieval.
Okay, so that's search. What about Analyst?
Cortex Analyst deals with structured relational data. Columns and tables, transactional figures, dates, numbers. The input here is a natural language question about the business, like what were sales last quarter in the North American region?
And the output is a direct answer.
A direct answer or a business insight. And it achieves this by generating and executing SQL code under the hood. Its primary function is analytics via LLM.
That clarity is essential. So if I have a database of millions of customer contracts and I want to find a specific clause, I use search.
Right.
If I have a sales table and I want the total revenue figure for Q3, I use Analyst.
Exactly. To summarize it for you listening, choose Cortex. Search for RAG, for document retrieval, for knowledge bases, anything involving finding text fragments. Choose Cortex Analyst for operational business intelligence, self-service reporting, and natural language data analysis against your relational data.
They're complementary, but they are architecturally distinct.
They're very distinct.
Okay, here's where we get to the technical decision point that really determines the quality, the cost, and the language support of your entire search service. We're talking about the engine driving the semantic search. the embedding model.
And this choice, as the source material really stresses, is critical because it's permanent for the life of the service. You can't just go in and modify the model setting later.
You can't.
No. You have to drop the entire service and recreate it from scratch, which means you're incurring the full cost and time of re-indexing all of your data. So you have to get it right the first time.
And we also need to remember that Snowflake charges based on usage specifically per token embedded by the chosen model. So a more sophisticated model often means a higher cost per token, which just adds to the importance of this choice.
It does.
So let's detail the 4 supported model options. Let's focus on the trade-offs and dimensions and, crucially, that context window size.
All right. We currently have 4 options supported natively for Cortex Search. Let's start with Model 1, Snowflake Arctic Embed-M v1.5. This is the default choice.
The one you get if you don't specify anything else.
Right. It produces vectors with 768 dimensions and has a context window of 512 tokens. It's also restricted to English content only. With about 110 million parameters, it's the lowest cost and fastest option. It serves as a really reliable general-purpose model for organizations that are dealing exclusively with English text.
So it's a good starting point, but that 768 dimensions means the semantic capture might be a little less nuanced than a higher dimensional model, and that 512 token limit is a major constraint we are definitely going to talk more about.
It is. So if you need higher fidelity or multilingual support, you move to Model 2. Snowflake Arctic Embed LV 2.0. This increases the vector dimension to 1024, which provides a richer, more nuanced semantic representation.
A bigger map of meaning?
A much bigger map. It's a much larger model with 568 million parameters, and crucially, it supports multilingual content. Its context window, however, remains at that standard 512 tokens.
And that increase from 768 to 1024 dimensions is subtle, but it's powerful, isn't it? It's like moving from a high-definition image to an ultra-high-definition image. You just capture more detail in the meaning.
That's a great analogy.
And if you're operating in a global organization or you're indexing customer logs in 5 different languages, this multilingual capability is essential, even if it comes with a higher cost per token.
Right. Now, Model 3 is the specialty model, and it directly addresses the biggest limitation of the first two, that context window. This is Model 3, Snowflake Arctic Embed LV 2.08K.
8K model.
Yes. It retains the 1,124 dimensions and the multilingual support of the LV 2.0 model, but the context window expands massively to 892 tokens.
That's nearly 16 times the capacity. This is so critical. For you listening, we really have to emphasize what that 512 token limit means in practice. If your source document is a 50-page legal contract, that's thousands of tokens long, and you use the default model.
The semantic vector that captures that document's meaning, it will only be derived from the first few paragraphs. The meaning contained on page 30 will be completely missed by the vector search component. Exactly. The 8K model is essential for any documents where crucial context can appear deep within the text. If you are indexing research papers or comprehensive technical specifications or large legal filings, you have to either use the 8K model or you have to perform extensive preprocessing and chunking of your document.
Right, chunking.
You have to do one or the other to avoid losing semantic relevance beyond that initial 512 token cutoff.
And that pre-processing is labor-intensive, so the 8K model really offers an architectural simplification, even though it will be the most costly option per token.
It's a trade-off. Finally, we had Model 4, Voyage Multilingual 2. This one is provided by Voyage AI, and it also offers 124 dimensions and a 512 token context window, and it's multilingual.
So what's the difference here?
This gives you an alternative performance profile to the Snowflake Arctic models. It's noted for its strong multilingual performance across very diverse global languages. So if your data involves particularly complex or, low-resource languages, testing this model against the Arctic LV 2.0 might be warranted.
So the key architectural decision really hinges on 3 factors: language, English versus multilingual; document length, that 512 token max versus the 892 token max; and of course, budget, the cost per token.
And you should always check regional availability. Not all of these models are available in every single region, and the final cost per token has to be confirmed in the consumption table before you commit to an architecture.
That makes sense. Since the embedding model choice is so critical and so permanent, let's now see how that selection fits into the actual deployment syntax. How do we turn our raw data into a functional search index? Let's get practical with the setup steps.
The process is remarkably straightforward, but it does have some prerequisites. First, you need an active Snowflake account and, of course, sufficient permissions. Specifically, that Snowflake.Cortex role is necessary to run the service creation commands. You also need a dedicated warehouse for compute during the indexing process. And if you want to take advantage of that incremental automated refresh functionality we talked about, the target lag feature, you have to ensure that change tracking is enabled on the underlying source table.
Okay, so once those prerequisites are met, the heart of the service creation is a single declarative SQL statement.
That's it. And that SQL statement is what defines the service's identity and all its parameters. You start by defining the service name, and then you specify the configuration in 4 main parts.
All right, what are they?
First, you define the core content. OnContent points to the specific text column in your table that you want to search within. This is the column that gets fully embedded and indexed.
Okay, that's the body of the text.
Second, the attributes. These are additional columns like a document ID, a title, or a category. They get indexed for quick retrieval, but not necessarily for the semantic search itself. These are used for filtering or for faceting the results.
Like only show documents from 2024.
Exactly. Or just for returning metadata to the user interface. Third, the operational controls. You set the warehouse that will supply the compute credits for the index building and refresh cycles, and you set your desired target lag, specifying your freshness policy.
1 hour, 5 minutes, whatever you need.
Right. And fourth, the actual source data definition, the AS select query. This query dictates exactly which rows and columns are used to populate the search index.
This is vital, isn't it? Because you can use this query to filter out irrelevant data, or join multiple data sources, or perform light transformations before you even start indexing.
You can. It must, however, adhere to the rules that govern dynamic tables, which means no non-deterministic functions. You have to ensure the source data is consistent. Once you execute that one command, the index building begins automatically, using your specified warehouse compute and embedding the text using your chosen model.
That sounds simple enough. But let's solidify this concept of semantic retrieval with that movie application example that was provided. This is the best way to understand how the hybrid search service acts on different types of queries.
Yeah, that's a great example. So imagine we've indexed a movie database, where the index content is the movie description, the cast, and the title.
Okay. Let's test the power of the components. Let's say a user is searching through internal corporate documents and they query the exact phrase security incident response. Where does the win come from in that case?
That is a fundamental keyword win. It's highly specific, low-context terminology. The parallel keyword search stage ensures that documents matching those specific exact terms are retrieved with high precision and ranked appropriately. The user gets the reliable expected outcome.
Okay, makes sense. Now let's switch to a query where semantic meaning is paramount. Something like space exploration wormhole future planet. This is highly conceptual, almost philosophical.
This is a definitive vector win. No document title is likely to contain that exact phrase. The vector component, having captured the concept of theoretical physics and interstellar travel, will retrieve a relevant sci-fi film like Christopher Nolan's Interstellar.
Because the engine understands the underlying concept.
Right. It's the concept described by that abstract string of words.
Okay, what about something that requires a more nuanced understanding of tone and genre? Like if I query for dark superhero stories.
This is a great test for the subtle intelligence of the hybrid model, and especially that re-ranker. Cortex Search understands that dark implies a certain tone, a mood, a genre. It successfully retrieves a movie like The Dark Knight.
And the re-ranker.
The final re-ranker stage ensures this film is prioritized, even if the word dark doesn't actually appear in the description. But terms like gritty, vigilante, or serious drama do.
And finally, let's go back to the example that encapsulates the combined power, querying dream heist movie.
This one beautifully demonstrates the conceptual linking. The engine links the disparate concepts of dream, so surrealism, subconscious and heist planning, execution, high stakes, and it successfully retrieves inception. This is where that cross-encoder re-ranker truly shines.
Because it confirms the conceptual fit?
It confirms that the conceptual fit between the query and the documents is the highest, and it places it right at the top of the result list, delivering the most meaningful answer. These examples really prove that Cortex Search isn't just running two simple searches side by side. It is intelligently synthesizing the results to provide a quality that goes far beyond traditional retrieval methods.
Okay, we've established that Cortex Search is powerful, it's native, and it's high quality. But any serious deep dive requires us to confront the practical realities, the costs, the hard constraints, and the security implications. So let's start with the economics. How exactly does Cortex Search incur a cost? The source material details 5 distinct components.
And understanding these 5 components is absolutely non-negotiable for architectural planning and for budget forecasting. It's a bit complex because it involves 3 different charging models.
Okay, let's break it down.
Cost component 1, warehouse compute for index building and refreshing. The initial heavy lifting, reading all the source data and running the embedding models for the very first time, that requires a standard Snowflake warehouse.
And the refreshes, too.
And the subsequent incremental refreshes, driven by target lag, also use this warehouse. This is charged based on standard credit consumption. So optimization here means choosing an appropriately sized warehouse and setting an optimized target lag.
Makes sense. Cost component 2.
Token embedding charges. This is the direct AI cost. Every time new or changed text is processed, Snowflake bills you per token embedded. And since the context window for a document can range from 512 tokens all the way up to 892 tokens, the choice of the embedding model dramatically impacts this cost component.
As does the frequency of change in your source data.
Right. Now here's the component that often catches users by surprise because it's an architectural commitment. Cost component 3, the multi-tenant serving layer. Cortex Search is served by a highly optimized, high-availability, low-latency multi-tenant layer that's managed entirely by Snowflake. And for that, you pay a continuous monthly fee per gigabyte of indexed, uncompressed data.
Wait, I need to zoom in on continuous monthly fee. This means that unlike the compute cost, which is episodic, it only runs when data changes, this serving cost is incurred $247 as long as the service is active, regardless of how many queries you run.
That is correct. It's the cost of keeping that index highly performant and instantly accessible. This is a critical factor in your total cost of ownership, your TCO. If you build a massive 200 gigabit index and you only query it 10 times a month, that monthly serving layer fee will dominate your cost structure, even if your compute and embedding charges are minimal.
So that mandates strategic indexing. You should only index what you truly need to search.
It puts a lot of pressure on the listener to be very precise about their data selection in that Avis select query. If you index extraneous documents, you're just inflating that continuous monthly fee unnecessarily.
Okay. And the last 2 components.
The final 2 components are more standard platform costs. Cost component 4 is the standard Snowflake storage fee for the physical index data itself. And cost component 5 covers the minimal cloud services overhead used for things like change detection and scheduling refresh cycles. That's only billed if it exceeds the standard 10% compute threshold.
So the big takeaway on cost is that Cortex Search has a continuous commitment cost that has to be factored into the annual budget. It's a key difference from just standard warehouse credit usage.
Absolutely. The decision to maintain an active Cortex Search index is an ongoing operational expenditure, not just an episodic compute cost.
Okay, let's move to the constraints. These are the project killers if you don't account for them early. What is the fundamental physical limitation users face when defining their source data?
The primary physical constraint is the base table size limit. The total row count that results from the service's source query, that direct select statement, must be under 100 million rows.
That's a hard limit.
It's a hard limit. If you attempt to index 100,001 rows, the service creation will fail immediately. This is a current non-negotiable ceiling, and it forces organizations with multi-billion row tables to strategically filter and segment their data before they can index it.
That forces data teams to make some tough choices about which documents are essential for semantic search versus which can just remain on the structured layer.
And the second major constraint ties directly back to our model discussion, the token context window defaults. We have to repeat this. For the standard lower-cost models, the MV1.5 and the LV2.0, only the first 512 tokens of text are used to create the semantic vector.
Let's put that into perspective again. If you have a document that is 10 pages long, the semantic understanding, the fuzzy search magic, is derived only from roughly the first 1 or 2 paragraphs. So if the core concept or the answer to the user's question is on page 7, the vector search component will miss it entirely.
That is the architectural implication. While the entire document text is indexed for keyword searching, that superior semantic capability is just neutered past token 512. And this constraint dictates a clear mandatory requirement for any organization dealing with long-form data.
You must either absorb the cost and complexity of the 8K model,
Or you have to institute a robust pre-chunking strategy.
And pre-chunking means splitting those long documents into smaller, semantically distinct fragments, like breaking a policy manual into individual 500-token paragraphs or sections defined by headings.
And then indexing each of those fragments as a separate row. Correct. This ensures that every meaningful section of the document has its own high-quality semantic vector, which maximizes your retrieval accuracy for long documents.
But it moves the complexity from Snowflake's Cortex Search back to the user's data ingestion pipeline. It's necessary for optimal performance with long texts, though.
It is.
What other technical limits should the listener know about?
Well, first, the source query has to strictly adhere to those dynamic table rules, so no non-deterministic functions. Second, some operational concerns. The service currently cannot be cloned or replicated via standard Snowflake commands.
That's a big deal.
It impacts how you manage failover or promote indexes from a development to a production environment. Third, and this is critical, you are locked into the provided embedding models. There is no support for custom or external models available at this time.
And finally, let's address the permissions and the single largest security caveat in this entire deep dive. We know we need Snowflake.Cortex user to create the service and usage to query it. But the source data security profile is, well, it's compromised here, isn't it?
This is the most important security warning for any enterprise deployment. Cortex Search services do not respect row-level security, RLS.
That is a staggering operational detail. So if a table contains sensitive data and I have RLS policies set up so that only managers can see salary information and I index that table, the RLS policies are just ignored.
They are. The search service indexes all data it is granted access to when it is created. Queries against that search service then run with the authority and rights of the service owner, thereby completely bypassing any RLS policies defined on the underlying source tables.
This means if an organization relies on RLS for data segmentation, say, separating data by geographical region or by sensitivity level, they cannot index that data in a single Cortex search service and grant broad access to it.
That is absolutely correct. If that data separation is mandatory, the organization has two options. One, ensure that the AS select query explicitly filters the source data down to only the information that is safe for the least privileged user of the service to see. Or two, the organization must architect a solution where they create and manage separate Cortex search services for each necessary access tier, ensuring proper role-based access control is granted only to the service itself, not relying on the RLS underneath it.
It requires a specific, explicit security strategy that has to be designed into the architecture from day one. You absolutely cannot assume RLS will protect sensitive data exposed via Cortex Search.
Not at all.
This has been a necessary deep dive into architecture, the capabilities, and the critical constraints of Snowflake Cortex Search. We've confirmed that this service successfully solves the challenge of messy, unstructured data by delivering powerful, high-quality hybrid search natively within the Snowflake environment, saving organizations weeks of custom development.
Yeah, it delivers search quality that combines the necessary reliability of keyword matching with the superior accuracy of semantic understanding. And it does that through its unique three-stage process involving the vector engine, the lexical engine, and that final neural re-ranker.
And by being fully managed, it just drastically reduces the TCO burden associated with managing external vector databases and those complex synchronization pipelines.
It really does.
Before we wrap up, let's leave you with one final thought to mull over. We've highlighted two major constraints: the firm 100 million row limit and that pervasive 512 token context window default for most of the models. How may your organization strategically choose which massive long-form data sets, say a decade of financial reports, to index immediately versus those that demand architectural preprocessing?
Specifically, you should think about the trade-off. Is the continuous monthly serving cost of that expensive 8K model less than the engineering effort required to build and maintain a sophisticated data pipeline that automatically chunks those long documents into 512 token segments before you index them into a cheaper model?
A decision to chunk or to pay for 8K is going to ultimately determine your retrieval quality, your time to value, and the true total cost of your Cortex Search deployment.
A lot to think about there.
Food for thought indeed. Thank you for joining us for this deep dive into the architecture and practical realities of Snowflake Cortex Search. We hope you feel thoroughly informed and ready to start planning your next search strategy with confidence.
Until next time, keep digging into your data.